Hey everyone, let's do a quick summary of the first derivative rule, and then we're going to talk about what the second derivatives tell us in regards to graphing. So what we learned in our first lesson is that when your slopes are positive, so when your slopes are positive, your function is increasing, and when your slopes are negative, your function is decreasing. And what happens when you go from a region of increasing slopes, positive slopes, to negative slopes, you got to pass through a zero slope. So you go through a maximum. And when you have negative slopes or a decreasing function and you go to positive slopes, you again pass through a zero slope because going from negative to positive region, you got to go through zero, gives you a minimum. So we're concerned about what we call critical numbers, where your slopes are zero, or we're also concerned about critical numbers where our slopes are undefined. Because if you don't have a point there, you don't have a slope there, your function is not increasing or decreasing either. So that's kind of what the first derivative tells us. It's all about the slopes. The second thing we're going to look at is the second derivative. And what we're going to talk about with the second derivative is how your tangent lines are above the curve or your tangent lines are below the curve. And when your tangent lines are above the curve, it's like they're pushing the curve down. And the function in this region where the tangents are above is called concave down. And then when the tangents are below the curve, it's in this region, they're pushing the curve up. So this part of the curve is concave down. So we also have critical numbers for our second derivative, just like we have critical numbers in the first derivative. So we want to know, where is the second derivative equal to zero? Where is the second derivative undefined? Because where it's not zero, where it's not undefined, the second derivative is either going to be a positive value or it's going to be a negative value. And what we find out is if you were to find the second derivative in all these places where you're concave down, your second derivative in all of these places, when you calculate it, and we'll do this later on in an example, all these second derivatives are negative. So when your second derivative is negative, your function is concave down. And on this side, where the tangents are all pushing up, where it's concave up, the tangents are below the curve, we're pushing up. That's always the case when your second derivatives are positive. So if you have a positive second derivative at a point, so right here where your slope is zero, the second derivative is positive, you can use those thoughts to tell you that's going to be a minimum value because you're concave up with a zero slope. Here at this point where you have a zero slope, if you were to find the value of the second derivative at this point, this second derivative is going to be a negative value. So you're in a region of concave down with a zero slope. You're at a maximum. So that's what we're going to try and work on for the next lesson. And of course, this little purple point right here is the boundary between the tangents being above the curve to the tangents being below the curve. So that would be a critical number of zero in this case. We call that a point of inflection. The tangent lines go from being above to tangent lines going to being below. So that's just a quick overview of first derivatives and second derivatives.